So good afternoon, everybody. I'm going to deliver the second lecture of my series, and this one is going to be on the first stars in the universe. So, a cosmic event, the first stars. And it's a story of how one looks with telescopes from the ground in space, and how one has to look not just at the usual optical wavelengths, but also in the infrared. And so let me begin by showing you an example. So here is something that all of you, many of you must be able to recognize: Orion, constellation of Orion, the famous belt of Orion. And tucked in near the belt, there's a cluster of stars and a nebula. Now, you can't see this with the naked eye. You just see the odd star or two there. Even with an optical telescope, you can resolve a whole bunch of stars. But if you look in the infrared with a space telescope, this is what this region looks like. And this is all nebulosity being glowing because of the presence of stars, which we can't see directly. And this is the sort of place that stars are being born. And what I'm going to tell you about today is the birth of stars, and in particular, what about the first stars? What do we know about them? What can we imagine from our data? Okay, so let me begin by showing you a glimpse of the entire Milky Way as seen with a very different astronomical detectors and wavelength frequencies, okay? And so each of these strips is the Milky Way in the sky, as seen with radio telescopes, special hydrogen telescopes, and the good old optical. So this is what you see when you make a map of the Milky Way with standard, an amateur telescope. This is what you see. This is the Milky Way. You don't see these black regions, which are dense clouds of obscuring dust, but all of this other stuff is the well-known glow of the Milky Way. And what is amazing is that the Milky Way looks so different as you go from the longest wavelengths, the radio, the lowest frequencies, to the highest frequencies, X-ray and even gamma ray. And all of these features mark regions where stars are being born, and where there's lots of dust. Okay, in the infrared, basically dust heats, it traps radiation from stars, it glows, and so you see this. You can pick out this concentration, which we call the bulge of our galaxy. And when I show you a picture of other galaxies, it's a well-known feature. This central, huge numbers of stars, billions of stars, which you can't resolve directly, but they contribute to this light that you catch in the infrared. In the optical, of course, you don't see it. You can't see into the center. There's a lot of obscuring material in the way. And so these are more nearby stars, but this is the Milky Way. Okay, this is sort of the inferred shape of the Milky Way, and you put everything together, a central bulge and a disk, and then outside here is what we call the halo of the galaxy. Anyway, that's just a remark or two about the structure of the Milky Way. Okay, so my lecture today is about stars. That is just to set the background. We live in the Milky Way. We can't escape from it. It's both a thing of beauty and also a contaminant in stopping us seeing things that we might like to see further away. So there are, or even in the depths of the Milky Way. So one has to explore all of these many frequencies, different types of telescopes, to pull this picture together. Okay. So what is a star? I'm going to try to describe that. We, are made from the ashes of stars. Stars lived and died, exploded. Our sun is a second generation object made from the ashes of other stars long since gone. And if it wasn't for that, we would not be here, because the carbon in our bodies, the stuff that we're made of, comes from the deaths of stars, as I will try to describe. And so I'm going to have to say a bit about that, and the goal of this talk is to tell you about the first stars. I'm a cosmologist. I try to answer questions, not successfully, not because they're very hard. Where did we come from? And what is the universe made of? What is the future of the universe? These are the questions that are fascinating questions, and today it's going to be the past, the stars. I'm going to try to make that connection for you. How far can we go back in time and we look at stars? Now, what do we try to do when we study stars? So we try, it would be wonderful if you could say from very simple first principles, what determines the mass of a star? The sun, our sun, is sort of a standard unit. I mean, some stars are heavier than the sun, some are lighter. Typical stars are not that far away from the sun. Maybe the typical Milky Way star is half the mass of the sun. And it would be interesting if we could actually understand why the sun is so enormous. And it is enormous. It's 1 million times the mass of the Earth, for example. That's what the mass of the sun. And also, I showed you the glimpses of the Milky Way. We'll see more in a moment. But stars are being made everywhere where there's the material to make them, that is gas clouds, which collapse and make fragment, make stars. Do we understand the efficiency at which you can make these stars? And how rapidly all this happens? Well, we've been studying this problem now with the best telescopes that astronomers have, they can be provided with, and the answer to all these questions is no, which is a bit disappointing, you might think, okay? And the thing that's missing is that we don't really have a robust theory of star formation. Now, let me just say that we don't have a robust theory of predicting the weather, okay? That's incredibly complicated. And I'm going to show you pictures of the interstellar medium where the stars are being made. And you can see you have the turbulence, all of this complicated phenomena. Very, very hard to model. We just are far away from being really predictive, okay? Nevertheless, having said that, there are some key ideas, and I'm going to show you one or two, which are universal ideas, have been thought about for a long time, and give us a basic glimpse as to what might be out there, or why there are stars there. Okay, so let's begin with this man. So Isaac Newton, of course, is famous for having, sitting in his garden, staring up at apple tree and so forth, and figuring out that there was some gravitational force that directed the apple down to the ground, etc. So he is responsible for the theory of gravitation. And he also worried a lot about why there were stars and there were planets in the universe. How did this happen? So here is some correspondence that he had with a clergyman in 1692 who was very interested in gravity and science and the origin of things. And so what Newton wrote about was this. He said, imagine matter being uniformly spread through an infinite space. How on earth would it contract or fragment into something? He said, well, he had the idea that it would fragment. It would never all contract into one lump. It would contract into many lumps, okay? Some into one mass, some into another. And you might have an infinite number of great masses all over the place, okay? All that infinite space. And thus might the sun and fixed stars be formed, supposing the matter were of a lucid nature, because the stars are shining. Now, he then ran into a problem in the second part of this correspondence. I think a few weeks separated this. He said that, well, what about the planets? They're not shining, they're opaque. So if I have a theory that can explain why things make stars, why on earth would I make planets, relatively opaque objects? It was obvious that planets were things that were shining by reflected light from the sun, even then, okay? And he gave up at this point, and he said, let me, infer the counsel and contrivance of a voluntary agent. He was a religious person, and I think he was referring to his God, basically. But not all scientists stopped at that point, but it did take a while. It took about 200 years or so for James Jeans to come along. And Jeans was very much an agnostic, and he was a mathematician, a very skilled one, and a great popularizer also of astronomy. And what Jeans realized and demonstrated was the idea of fragmentation. So it was one of the missing links. He took Newton's idea and developed it into a scientific theory. Okay, and this scientific theory was that you would automatically break up, because of gravity, into lumps, okay, that could potentially be the planets and the stars. So his view was that he can make planets, stars, etc., out of initial chaos. And he said, the great architect of the universe now appears as a pure mathematician, right? So that was a different perspective. And he basically used the idea that what determines a star is the struggle between gravity, which causes things to contract and break up and contract, and pressure, which stops it. So it was two opposing forces. And so genes worked out the condition for gravity to win. And we call this condition the genes scale, the genes length, the genes criterion. Famous for that. Okay. But he didn't get to the point that puzzled Newton about why planets, why stars, why opaque things, why do stars shine. And so this is a bit of an Anglo-centric talk actually, because the person who came along and solved that question was a great astronomer called Sir Arthur Eddington, who directed the observatory at Cambridge for many years. So when he was in his 20s, that was the time of the First World War, and he refused to go into military service. He was a Quaker, and he managed to, as a conscious objector, persuade one of his colleagues, Astronomer Royal at that time, to appoint him on an expedition, this is in 1919, to go and measure during an eclipse the bending of light by the sun when it eclipsed the stars. Because Einstein's theory had just been announced 2 or 3 years before, and no one really believed it, but there was a prediction Einstein made, light should be bent by gravity, and Eddington set out to run that expedition. And amazingly, he found the effect and Einstein became famous overnight, and so did Eddington, for having confirmed the theory of general relativity, the bending of light, one of the predictions. It was a complicated theory. Amazingly, after the announcement at a press conference, a reporter came up to Eddington and said, I have heard that only 3 people understand Einstein's theory of general relativity. Is that correct, Professor Eddington? And Eddington scratched his head for a moment. Well, I can only think of 2 people. Okay, but anyway, he was a great man. He had a number of more controversial ideas. This was one of them, which he spent, it so happens that great scientists, after some number of years doing amazing things, do sort of go out of the mainstream to follow their own rather curious things. Fred Hoyle was a great example of this, but let me not discuss Fred Hoyle today, but Eddington. So Eddington had a fundamental theory, a theory of everything. And this theory led him to predict the exact number of particles in the universe, and there it is, okay? Now, no one, I think, has ever managed to decipher the full extent of Eddington's reasoning, and it's a theory long since forgotten, and it makes predictions that, in fact, are not true, other predictions. But anyway, what he did that's relevant to this lecture was a most amazing prediction that has been verified. And so he said that, imagine a physicist living on a planet always cloud-bound. You could never see the sky, okay? And he said this physicist could predict there had to be stars out there, okay, just from pure reasoning of physics, simple physics. And let me just say, this was long before we had the slightest idea of why stars shine, of the source of energy in the stars, which we know is nuclear reactions, burning of hydrogen, just as we have in hydrogen bombs, but in a more controlled way inside stars. But that theory had not even surfaced, so he had no idea what controlled this. But he did know about gravity, and he knew that for a star to shine, radiation was coming out, and the radiation has pressure, pushes against the atoms and the ions and all that stuff. And so a star was a balance between gravity and pressure. And so using that simple reasoning, he said, well, imagine a series of globes, of giant gas globes, okay? And we start with the smallest ones, maybe 10 grams, go all the way up to some enormous number, okay? In fact, up to, and this is the power of 10 of the size of that globe. So 10 grams is 10 to the 0, 100 grams is 10 to the 2, okay, 10 to the 1, sorry. And then this is 10 raised to the power of 33. And he said that only in this range of enormously massive gas globes could you have stars, because if you make them too massive, they're so hot they blow apart from radiation. If you make them less massive, they're just too cold to be able to shine properly. And so he had a very limited range. And what's amazing is that this is the stars. This is the entire range of masses of the stars. We draw aside the veil of cloud beneath which our physicist has been working, and let him or her look up at the sky. There he or she will find 1,000 million globes of gas, nearly all of mass between its 33rd and 35th globes. That is, say, between 1/2 and 50 times the sun's mass. And this, in 1926, was revolutionary, long before we knew what powered the stars, but it's true. Amazing. Okay, well, then, just to take this one step further, and this is about as technical as this talk will get, I explained that a star was this balance between gravity and pressure, okay? The pressure of the electrons, basically, which are whizzing around at a higher speed than the protons. So it's this struggle. It turns out you can describe this balance between these two forces. Gravity is a really weak force, okay? Electromagnetism is a strong force. How on earth can you balance them? Well, the point is that if you think of electrons and protons, they have charges that cancel each other out. So it's only the odd electrons in an ionized plasma that give you pressure. And so and at the same time, gravity does not cancel out. The gravity force is tiny between two protons, but have so many protons, it adds up. And that's why there's some tiny number that compares the ratio of the gravity force, electromagnetic force, but this number is what determines, when you add it up with many atoms, the mass of a star like the sun. And so, as a result of all this, the theorists concluded over the next 2 or 3 decades that there are basically 3 important masses for stars that come into our understanding of the birth and the death of stars, especially the death of stars. So we call the biggest star that we can ever expect, because it will blow itself apart by radiation, the Eddington mass, about 100 times that of our sun. We're well below that limit. The smallest star that can ever burn hydrogen is roughly 1/10 the mass of our sun. We see many of those around us now with the telescopes, which we didn't have in those days. The powerful can see those stars, the smaller ones. And what about the ultimate limit for the end point of a star? This was something discovered by an Indian astrophysicist who came to work with Eddington, called Chandrasekhar, and that is called a white dwarf star, and that's about 1.7 solar masses. So that's what our sun will end up as, a slightly less massive white dwarf. When it's totally run out of all its nuclear power, nuclear fuel, that's the fate of the sun. Incredibly compact object. It's called a dwarf because it's so compact. All of the sun will contract into something roughly the size of the Earth. Okay, and the sun is now much, much larger, of course. Okay, so what determines the mass then? I've explained. How long does a star last? So what you have now is this burning of hydrogen. Hydrogen turns into helium. Helium atoms weigh slightly less than the 4 hydrogens that go into them, 4 protons and electrons, and the missing mass via Einstein's famous equation E = mc² gives me energy that powers hydrogen bombs and also powers future thermonuclear reactors, which we'll someday in 100 years maybe have on the Earth to solve the fossil fuel problem, because we have an ample supply of water out there. And that is hydrogen. But for our purpose, it's controlled inside the star. And the amount of fuel we have in the sun just depends on the mass of the sun. So roughly maybe it's the center of the sun, 1/10 of the mass of the sun is potential fuel. But the problem is that stars are very profligate users of their fuel supply. And the luminosity of a star rises very strongly the more fuel there is. It goes roughly as the cube of the mass, okay? So this means that if I now ask, how long does a star live? The sun is going to live for another 5 billion years. No hurry. But if I have a star that's 10 or 100 times more massive than the sun, it's going to live a much shorter time. In particular, if I have 100 times the mass of the sun, the most massive stars we know, they will only live 1 million years. Then they've run out of fuel. Then they must explode, okay? And because this is such a short time scale, cosmically speaking, the Milky Way's been around for many billions of 5 billion years at least. So 1 million years is the twinkle of an eye. That means we should see stars dying all the time we look out. Okay? It should be a fairly common event because there are so many stars around us in the Milky Way. Okay, let me then begin. Before I can get on to the first stars, let me say a little bit about the sun, okay? I'm going to show you some pictures of the sun. You know, we all have this nice image of the sun as the source of our fuel. It looks like a nice gentle orange globe in the sky, right? But in fact, if you look at other wavelengths, it's rather different. And so these are some views of the sun. The color scheme is slightly artificial, so just ignore the colors. But these are ultraviolet views of the sun taken by satellites. This is an X-ray view of the sun. You see this immense activity. This is a giant solar flare, okay? And at this time, you can see these eruptions from the surface, these loops from the corona of the sun. These are violent storms going on in the sun. It's a very violent place. And depending on the stage of the solar cycle, we have more sunspots or less sunspots, because that changes every 11 years, you can be in a peak phase or a lower phase of solar activity. And as you may recall, when the sun is going through peak activity, as in this image, that does affect radio communications on the Earth and so forth. So it does have impact by disrupting. And then in the X-rays, you can see this is really hot gas one sees in X-rays, immense explosions, again, which can leak out and affect, even though we're 96 million miles away, it can affect kilometers away, it can affect our... Okay, here's a beautiful quote from the founder, the co-founder of the theory of the Big Bang. So Lemaitre, who really was someone who had the grand vision of things, he was ordained as a Jesuit. Just about the same time he had worked on the theory of the Big Bang and continued to work in cosmology for a long time. He said, "The evolution of the world can be compared to a display of fireworks that's just ended. Some few red wisps, ashes and smoke. Standing on a cooled cinder, we see the slow fading of the suns. We try to recall the vanished brilliance of the origin of the worlds. And we have that possible origin of the worlds by seeing these short-lived stars, star death. And we can even witness star birth." Okay, let me give you one more explanation of how we try to understand how stars are made, and after that it'll be much less technical. But I want to go beyond miracles and try to demonstrate that one needs a little more than the genes Newton idea of things fragmenting. Eddington's ideas were very important, but there's some new ingredient one has to add to understand stars, and this is why, okay? So if I take, and this is the most technical slide I'm going to show you today. So if I imagine this genes optimal scale that James Jeans said, this is where gravity and pressure balance, okay? Imagine my interstellar cloud, as it contracts, getting denser and denser. It'll break up into these bits, okay? And because it's getting denser, gravity is dominating more and more, so this gene scale should be getting smaller. So it should fragment. But there comes a time at which this cloud is so opaque, so radiation cannot escape anymore, so you stop the fragmentation. You have to be able to let energy escape to be able to get denser and denser. The energy's got to go somewhere, and if you can't get out, tough, that's the end. And so what Jeans basically said was that there's a minimum value, and this typically should determine of the fragments that can form, and this should be the mass of a typical star. Well, it's interesting, as we now put in much more detailed calculations via big computers of this argument, it's been realized that this is off by a factor of about 100. Now, this may not seem terribly, given that I said we don't know the theory that well, alarming, but it is a cause of serious worry for the for my colleagues who do these wonderful numerical simulations. I'll show you one example in a moment of how structure-formed stars form, because it should be more like 1 times the mass of the sun, and it only involves, this fundamental constant I mentioned. So this is a nice result, and it turns out to be verified by all we can do, but it's the wrong answer. Okay, so what is going on? So the answer is we've missed out an important piece of physics. Okay. And that physics is that as these fragments form in some collapsing cloud, they will grow. And we call that, by gas falling in, we call that process accretion. Okay? So these accrete, and then you come into another problem immediately, because if they keep on accreting, they maybe grow too big, okay? Because this cloud is maybe millions of times the mass of the sun. That's typically what we see. So what stops them? So it gets even more complicated. Not only do we have to add to fragmentation the concept of accretion, but we have to add another concept called feedback, which stops them. Something, when you have a star putting out enough energy, stops the stuff falling in, stops it growing. So that's sort of where we are. And this reasoning leads to one very important prediction, okay, which is relevant to my talk, the first stars. And that prediction is the following, that in the beginning, when I had none of this exploding star contaminating the gas, the raw stuff that's out, the material that's out there, I just had hydrogen and helium. That was it from the Big Bang, okay? The helium was made in the first minutes, about, 30% by mass, but mostly it's hydrogen. Well, because I don't have the heavy elements are great seeds for enabling gas to cool down. So because I don't have that contamination, which can act as seeds for cooling, the first stars form from very hot gas, okay? And because they form from very hot gas, that means pressure forces are much more important. Therefore, the first stars were big stars, were massive stars, and they were very short-lived. So this is a simple prediction, verified now in great detail, that the first stars, unlike our sun, were 10 or 100 times the mass of the sun, and therefore had a very short lifetime. It's a good thing, because then they could explode and seed their metals or whatever, their debris, and make way for the next generation. So that's sort of what we think goes on. As far as this process that stops stars growing too much, I'm just going to show you results of simulations on computers which explain how this works. And it's complicated because this is where magnetic fields come in. So magnetic fields are everywhere in space. We see them in all interstellar clouds, throughout the universe, even in other galaxies. And they basically resist gravity as well. They give you another sort of pressure that's, in some sense, even more powerful than just the pressure of the radiation, because this would apply to the lower mass stars where there's not much radiation. And so these are magnetic lines of force, and if I zero in, you can see they basically, as this gas wants to contract, the magnetic field lines sort of give you some resistance, and that stops stars growing too big and slows everything down. Okay, so now let's get back to a slightly more pictorial approach to the universe. I want to just give you some glimpses, using beautiful images of how stars are conceived, are born, age, mature, and die eventually. And the first thing you have to be aware of is that this is a picture taken with a Hubble telescope of an area of stars, and the brighter ones are the younger stars, older ones. But when you look in the infrared, you see this, okay? Dust is everywhere, okay? So you have to bear in mind when you try to solve the jigsaw puzzle of how structure formed, that you have to be very careful what you look and how you look, and you have to piece this together. I mean, this dust, is important. The planets, our Earth, formed from the dust in the early solar cloud that formed the sun. So this stuff is crucial, okay? So you have to have images that control all of this. Okay, right, so let's then move, first of all, to how you can make a numerical simulation. This is what theoretical astronomers love to do. You take the biggest computer you can get, and you try to I've just given you by physics standards, very simple arguments, but you can make things much more precise. Now, computers are limited. They're not quite big enough to really get into the fine details, but because the first stars should have been simple, there was no dust and so on, maybe no magnetic fields, none of these complications, then it's just hydrogen mostly, helium's pretty inert, you should be able to simulate it. So here's the sort of thing one can do. And so this simulation is powerful. It goes from light year scales all the way down to basically the distance of the Earth from the sun, and so-called astronomical unit. And you're zooming in, it's an adaptive simulation, you're watching the fragmentation, fragments are forming out of this kind, they're breaking up into smaller fragments. And you're left with something which eventually is going to be your massive star. Okay, we haven't quite got there yet, because this would mean going another factor of 100 or 1,000 in resolution, and this, when this was made, they couldn't quite do that. Okay, so that's how you can persuade yourself that while my arguments so far have been, in physics we sometimes do what is called the spherical cow approximation, right? Someone says, demands a physicist to give him a model of a cow so he can predict the amount of milk production, and he comes back with a simple spherical sphere and it says, this is my spherical model approximation of a cow, and so forth. Now, this sort of simple modeling is replaced now by detailed computer modeling. May not work for a cow, but it does work for gas clouds. Okay, and stars. So then from this we can confirm the first stars are hundreds of times the mass of the sun. And we can simulate these things. So how do we actually go out and look for these things now? This is the theorist's dream. What do we do? So how do we find traces of the first stars? Well, it's clear, theory tells us they were massive and they were short-lived. They lived billions of years, okay? And so they exploded, they produced various elements heavier than helium, iron, carbon, whatever, which then polluted the medium around them. And then this medium could then cool and fragment much more efficiently and make the next generation of stars. Okay, and then you have, the current star formation, which includes stars of all masses. Okay, so the trick is the following. There should be fossils left over, because these stars which are massive have a particular signature of producing maybe a little oxygen, a little carbon, but in different ratios from what the whole range of stars would do, as happens today. So there's a unique chemical signature to the first stars. Even though those stars have long gone, you can look now around our Milky Way for the older stars and look in their spectra. We take spectra in astronomy with big telescopes to see what evidence there is of something unusual which might be the relic of the first stars. I should say that spectroscopy, an invention of the 19th century, is an amazingly powerful tool. Helium was discovered in the sun before it was found on the Earth, okay, to give you one wonderful example, thanks to getting spectra, okay. And it's the second most abundant element of the universe. Okay, so here is the third oldest known star in our Milky Way galaxy. So it's not in any particular place, it's well out in the middle of nowhere. How do we know it's so primitive and old? This is a rather typical star, okay, which already is primitive in that it's the amount of iron in this star, it's a typical thing we measure in the spectra of stars, is already 1/10,000th of that of the sun. And you can see all of these this is wavelength, and these are absorption features, I mean, the sun is yellow because of sodium, etc., so they'll be strong. But you don't see much sodium in this old star, okay, but for the sun, you would get something, Okay, and then when you get down to this incredibly metal-poor star, 100,000th of that of the sun in the amount of metals, you see almost nothing, right? Only a little bit of iron, actually, but a tiny trace. And so we think this is one of the oldest stars. And by looking, and you do see some other elements in the stars, you see tiny trace amounts of some of these other things. And by studying those, you can try to see if it tells us something about the first stars which have long gone. Okay, in some sense, it's a fossil record of what happened. Just as you in archaeology, you look at fossil records, the nucleosynthetic signature, the chemical signature in the older stars, tells us what happened before. That's the hope, and we've been able to make some progress that way. Okay, so now I'm going to take a slight detour from the older stars because there is one new exciting thing I'll come to in a moment. But first, the detour is going to be stars, okay, how they form. So let's begin with the birthplace of stars, the womb of stars. So this is pictures by the Hubble Space Telescope, and this is a dark cloud, okay, incredibly dense, so opaque that light You can't see background stars. And within this dark cloud, we look in the infrared, you see evidence of young stars being born. Okay, and here's another example. These are foreground stars. In this region, stars are being born, maybe, and this is being irradiated by light from stars over here, which may have recently emerged from their own dark clouds. But this is a dark cloud, the womb where stars are being born, and we confirm this by looking deep inside with infrared wavelengths. Okay, what about birth? Okay, so evidently, at some point, the stars break out. And when they're young, they're more luminous than they are today, especially the more massive stars, which are very bright. And so here is a classical picture. Many of you have seen this, the so-called, dubbed the pillars of creation. And you can see stars basically emerging from these very dark birthplaces, dark clouds. And already all of this gas has been eroded by stars like this. It evaporates away, and here you see the remaining places where the stars will come out in the future, and you can begin to see. And another object. This is even better. You can see that again. Here is our dark cloud, and just beginning to break through over here is a young and rather massive star. It'll only live for 1 million years, so this is youth. These are babies. Okay, it's the birth of stars that we're seeing. So let's move on to youth. As the stars more and more come out of the womb, the dark clouds, then this is what we see. And again, you can see there are still traces of this womb-like material. The placenta of these stars, if you like, still hangs around in there. But many of these are now visible. Okay, so this is how things will look. Here's another example. You get these amazing images from the Space Telescope, right, which has been going now for 25 years. And this is in the Large Magellanic Cloud. There's a particularly massive set of young stars all together around a star cluster called Theta, and you can see all these stars have recently emerged from this is the youth of stars. Okay, let's move on to maturity. Okay, so now after a few million, tens of millions, hundreds of millions years, all this debris has been blown away, okay, ionized, evaporated away, and we're left with something like this, okay, field of stars, okay. So, these stars, many of them are tens of millions, hundreds of millions, and there are many even older stars, all, stars everywhere have had a birth phase, a youth phase, and now this is how the typical star field looks in the galaxy. But these are not the oldest stars. Okay, let me show you, finally, the oldest stars, okay? So the oldest stars in our galaxy are in clusters, which formed a long time ago when the galaxy was formed. And again, we don't really know the details, but we have ways of measuring ages, and we know these stars are almost as old as the Big Bang itself. So from the expansion of the universe, we infer a time when the universe began expanding, just from the rate of expansion. And that time is very, very close to the ages we infer, obviously slightly larger, but not by very much, and the ages we form for this star cluster, this so-called globular star cluster. And there are hundreds of these around the Milky Way that are in what we call the halo of the Milky Way, and that we study them. And also there are many stars out here, not in the globular cluster. These are so-called field stars. Also, most of them are just as old as this, outside this disk of the Milky Way where most of the current star formation occurs. So it's looking in our environment, outside our Milky Way that we see the beginnings, they're getting closer to the older stars. And when we want to look for fossils, we want to search either here or here for these very, very rare stars, okay, that might trace the missing stars from the beginning that have long since died. Well, what about death? Okay, now let me just show you how it is that stars die and why it is that we are so polluted with the remnants of these stars. So this schematically shows you how if I start off with hydrogen, as time goes on, the hydrogen in the middle is burnt. It turns into helium. More time, the helium is burnt, it turns into carbon, and so on and so on. And finally, you're left with an iron core. Now, iron is the most stable of all elements. thermonuclearly speaking, okay? It cannot give you any more thermonuclear energy, okay? And so you do, as you know, I mean, you have to go above iron to make an atomic bomb, to extract energy by unstable isotopes, or below iron for fusion. Iron is the ultimate slag heap of the universe, and at that point, the star there's no more pressure force from burning in the middle, the star must collapse, okay? And when it collapses in the center, that generates so much energy that blows off the outside. It's a huge explosion. Okay, and so what you blow off, you're left with mostly an iron core, and you blow off, carbon and nitrogen, oxygen, all the basic elements of life, needed for life, are blown off in this explosion, mix in with the surrounding interstellar clouds, and eventually will make new stars, which can be eventually like the sun. So is this just fantasy? Well, we see these explosions. Here's a beautiful example of explosion. So this was a galaxy studied in us. And then, suddenly one night they looked again, and over here, something happened. And this is a supernova explosion. It's almost as bright as the entire galaxy, right? The light in this is maybe 1/10 of all the light from the billions of stars in the galaxy. So brighter than 1 billion stars, basically. And so we detect these now in distant galaxies. They're used now in cosmology to even measure the size of the universe, because they turn out to be rather uniform sorts of explosions. But now it's commonplace. Exploding stars are seen very, very far away. And if you go back, 10 billion years, before the Earth was formed, but you can do that by looking deep into space, because light's taken 10 billion years to get to us. You can see these explosions happening now, and we can therefore infer that, long before our Milky Way formed, there were almost certainly explosions going on that seeded the gas cloud that eventually, was the Milky Way. Okay. Anyway, so the other way to study these things, of course, is to look nearby. So here's the most classic of all explosions from a star, the Crab Nebula, first recorded by the Chinese astronomers in approximately 1063 or thereabouts, okay? So there are records which tell you go into the constellation of this or that, and with their own Chinese names, of course, but one can now correspond that to modern nomenclature, modern sky maps, and you indeed, right at the location, seen by the Chinese, this star was very bright for a year and then disappeared. And we now know it all corresponds, because the expansion of this nebula also, it began about 1,000 years ago. It's moving at, thousands of kilometers a second, expanding out from the center. And there is even a tiny relic, a so-called pulsar in the very middle, which is the relic of the massive star that made the explosion. That's this compact thing left behind at the end that the iron core would create eventually when that collapsed. So there we are. That's the Crab Nebula, a famous supernova remnant. And then as time goes on, this explosion pollutes the surrounding medium. So this is an explosion, a supernova that happened the Crab was 1,000 years ago. This one happened 1 million years ago. No records. No one was around then. But we know it was 1 million years just from measuring the speed, okay, of the expansion. And so this is called the Veil Nebula. And then if I wait a little bit longer, you get things like this, okay, which are amazing. This is like, the ghost image almost of this explosion, which probably occurred about 10 million years ago. So, and all this debris, this contains not just hydrogen, helium, but metals, iron, nitrogen, oxygen, etc. It's going to mix in with clouds around here, and those clouds outside, there'll be other clouds, other explosions, will then collapse to make more stars. So that's the great sequence of events that awaits the Milky Way. But it doesn't await the sun. The sun will not be a supernova. It's not massive enough. It has a somewhat more gentle future. Okay, and here is the future of the sun. Okay, so in the center of this nebula, called a planetary nebula, is a white dwarf star. Okay, and the sun will turn into a white dwarf. It will first, however, become, as it runs out of fuel in the center, it will get hotter and hotter when it burns helium, takes more energy, and the outside of the sun will puff up. and this puffing up of the sun will encompass the Earth. It will burn everything on the Earth. It will become a red giant star. Okay, that's the fate of the sun in about 5 billion years' time. So we can't exactly ask our politicians to, worry about this. We should be asking them what to do, for the next 10 or 100 years maybe, but 5 billion, okay. But anyway, and presumably by then, if there is anything left on the Earth, we will have figured out how to leave the Earth behind and go for a happier place, right? Anyway, and when this happened, before then, lots of carbon in this nebula was ejected also. So stars like these red giants are a source of nuclear debris as well. Okay, so if I try to put this together, this is sort of the picture that we have. There's a wide range of masses of stars, and there's some range of masses that control the chemistry of the universe. And the most massive ones, when you look at far away, they're the really bright stars, and that's what you see, these young, short-lived stars. They control the light in the universe. So you have to dissect the light with spectra to see the chemistry. That's sort of the way we approach this. Okay, so how do we turn all of this into a theory of star formation? So this is a simulation by Ian Bonnell at St Andrews University. He takes a gas cloud and watches it fragment, and you're going to see stars are forming. And so this is, and here's the nebulosity, the remnants of the stars. So we can reproduce, the sort of things I've shown you images of in computer simulations now, okay, which take, weeks to run on the best supercomputers we have. But this convinces us the success in matching simulations, which obviously are not efficient enough to resolve every detail. We're missing a lot of things. Nevertheless, we believe that we're on the right track. Okay, so I've talked a lot about fossils. I've shown you a fossil, but there's one exciting new development I'm going to end up with, and that is, the question is, is there a way to directly see the first stars? Now, we call this population 3 of stars. Why do we call that? Because population 1, astronomers have this weird way of naming things. So population 1 is the disk. These are lookalikes of the Milky Way, okay? Not the Milky Way, but how we think it, pretty sure it is, when we dissect it in 3 dimensions with various telescopes. So this is the disk, full of young stars, very bright. And this is the bulge, and this is the halo. And the bulge and the halo are full of very old stars. And so we call the disk population 1. We call the old stars that we see, the ones I showed you in the globular cluster, population 2. And this hypothetical first star population we call population 3. Well, have we seen population 3? Okay, so there's one example just discovered in the past year. So I'm going to end with showing you that example. It's got a weird name. It's called CR7. I've forgotten why exactly. But it's at a redshift so far away in the universe. Redshift is a monitor of the expansion rate of the universe. Higher the redshift, the smaller the size of the universe. The universe then was about 1/8 of its present size. So this is a long way back in time. It's 1 billion years after the Big Bang, so 9 or 10 billion years distance away from us. This happened. And the weird thing about this galaxy, found with the latest telescopes, is that it has very strong emission lines in hydrogen and helium, which are much stronger than any metal line, anything due to metals. And this is thought to be a unique signature of the first stars when there were no metals present yet. And there may have been a few made by the odd explosion. And so this is a galaxy, okay? So in this galaxy, one finds it's incredibly strong, and this is a picture of it. You just see this blob on the sky, and one finds this incredibly strong hydrogen line. But what's equally dramatic is the strong helium line. All this other stuff is noise, essentially nothing else. And this is thought to be the signature of so-called population 3, the first stars in the universe. So we're seeing a galaxy worth of them dominated by these stars. Okay, so has yet to be confirmed. We've only one example so far, but it's a very exciting development that maybe we don't just have the fossils, but we have more than that. Okay, so to summarize, the first stars, I've argued, are long gone. They're very massive. but the polluted environment around them still survives. It's out there, and it contaminates intergalactic gas clouds. I haven't talked about those, but they're a way of also seeing things far away. You see gas clouds in absorption against the distant stars, the most distant stars in the universe, the so-called quasars. So you can study how intergalactic gas evolves in chemistry with time by looking far away. And they also contaminate the clouds around them, which then make the first modern stars, as it were, the second generation of stars. And we look for these stars by selecting very carefully. It's a needle in a haystack problem, but very few of those stars are incredibly low in metallicity in the halo of our galaxy. We find those, and we look for signatures in their patterns of spectral lines to learn something about the prior population. And so their abundance patterns trace the mass of the first stars, their fossils. And the most exciting development, only 1 year old, is that we may be on the verge now of discovering the true first star, a galaxy dominated by first stars. And the reason for that is that when you look back so far away, the light is highly redshifted. So we've only been able to do this experiment recently because up till recently we didn't have the astronomical telescope power to look in the infrared with very high spectral resolution. And that's only, that's very recent, incredibly elaborate and expensive equipment is doing this, but it's, one has the feeling now that a new era may commence in studying the universe 1 billion years after the Big Bang. So, thank you.